In this video, we'll be working with verifying identities utilizing the sum and difference identities. This is extremely important for me to state, and I've stated it before in previous videos, but for verifying an identity, your work is your answer. If there's no work displayed, there's no real answer. Okay? If you just simply identify that as, hey, this is an identity, check, move on, that's wrong. You have to be very clear about the fact that how is this side equal to this side? Or you have to be very clear about how does this entirety of the equation condense down to be this side is the same as this side. In any case, your goal is to make it very clear that these two sides are the same in some way. In previous videos, we covered basic verifying identities. It is possible to come up with a manipulation of this to get down to a single thing that is an identity, that is logically, yes, this is true. In a lot of cases, that's something like sine squared plus cosine squared equals to 1. If you got that in a previous example, such that that was what you ended up with, then yes, you verified the identity. You don't have to show that the two sides are the same, because those two sides are definitively the same. Now, one more time, reiterating everything that I've said in the last few videos for sign and difference identities. Anytime that you're manipulating the inside of a trig function, if this angle here is not necessarily the same as the angle that's in here, for verifying identities, your first goal is to make this inside exactly the same as this inside. Well, I can't just manipulate the cosine and distribute it through. Again, that's not mathematically appropriate. There's an identity that works with the cosine of pi minus theta. That identity is sitting right here, again, sitting in front of us, hopefully with our formula sheet out in front. So the cosine of x minus y, my x now is pi, and my y is theta. So I'm going to just go ahead and start by manipulating with just this side. Again, I want the angles inside this trig function to be the exact as the angle over here, which means I want this side to just end up having theta. Notice that there's a pi here, and also recall that pi is a value that's on the unit circle. So when I do end up condensing this into this stuff, or I should say expanding that into this stuff, I can simply evaluate the cosine of pi or the sine of pi. So let me go ahead and do this very carefully. My x is pi, my y is theta. So I'm going to have the cosine of pi minus theta is the cosine of pi times the cosine of theta plus the sine of pi times the sine of theta. This is all supposed to still be equal to the negative cosine of theta. Okay? So again, I've just carried this down, and I've changed this into this whole thing using this identity. Okay? This is one thing that you are allowed to do with verifying identities, is use previous identities you already know to be true to manipulate the thing that you're trying to prove. Now, the next thing I can do is I can evaluate certain pieces and steps. So the cosine of pi, cosine of theta, well, I can't manipulate the cosine of theta, but the cosine of pi I know is on the unit circle. It's this value over here, and that value is negative 1 comma 0, and the cosine at that location is the x. So the cosine of pi is really negative 1 times the cosine of theta. Now I want to make a point here really clear. And some of you can see this already, that as you start to play with this, it will condense very quickly down to this. And you'll notice right now, actually, that I have negative 1 times cosine. Hey, isn't that what I need? Which means that in this case, the thought process I want is that this whole thing should cancel out. It should become nothing. And if I do this carefully, you'll notice the sine of pi is this location here, which if I attempt to evaluate is just 0. So sure enough, 0 times the sine of theta is supposed to be equal to negative cosine of theta. Now at this point, because there's one step left, I would agree that yes, you're done. Okay? If you're not seeing this, you're not comfortable with it, 0 times anything is 0. Negative 1 times cosine of theta is simply the negative cosine of theta plus 0. That's all just going to cancel out, equals to a negative cosine of theta. And this is, again, notice one step to get from here to here. This is definitively done. This should be clear. Now, if you don't think it's going to be clear whether or not you're done with this identity, it's important to just show all the steps. Again, your work for these problems are your answer. Now, the next example we're looking at is 7b, and that's going to be the cosine of 4 theta divided by the sine of theta minus the sine of 4 theta divided by the cosine of theta equals to the cosine of 5 theta divided by the sine of theta cosine of theta. Now, in the last example, this one up here, I said it was important for us to get all these angle measures to be basically the same. So I used the identity to tear this thing apart into all these pieces. Now looking at these identities down here, you'll notice I have 4 theta as the inside of a cosine, I have 4 theta as the inside of a sine, so maybe I could just get everything to 4 theta. But then down in the denominators, notice I only have theta. These being different than these ones does make it a little problem for us. However, there's also a 5 theta sitting over here. So again, I'm focusing on the insides of these trig functions and noticing that I have a 4 theta, a 4 theta, a 5 theta, and a basic theta. And trying to get them all to be the same angle might be a trick or a tricky problem to handle. So what I'm going to do instead is I'm going to go ahead and just try and use some of my basic rules for manipulating trigonometric identities. And you'll notice here, again, this is something that is just a matter of seeing it, practicing it, playing with it, and making sure that you have seen something like it before. The fact that the denominator over here is sine and cosine, while the denominator over here is sine separately, cosine separately. So there's about 2 or 3 different things that I could do to try and move this thing forward. For instance, I could say, well, let's just try and break all this stuff down. I could take this cosine of 5 theta off to the side here, and I could say, oh, wait a second, this is the cosine of technically 2 theta plus 3 theta. I could tear this apart like this. Again, notice it's the cosine of that whole thing. Notice I didn't change inside to outside, I just changed the inside. And then I can use the identity here to modify that. But I think that's going to just cause more problems, because now instead of having cosine of 5 theta and 4 theta and 1 theta, I'm going to have 4 theta and 1 theta and 2 and 3 theta, which I don't think helps any. Now, we could continue this process by manipulating the 3 theta, manipulating the 4 theta, and playing with those in the same vein. So, for instance, I could change the sine of 4 theta to be equal to the cosine of 2 theta plus 2 theta. And doing so could actually manipulate, so eventually this 3 theta will end up being a 2 theta and 1 thetas, and hopefully things will simplify down. This seems like I'm rambling. The point of this is that there are a number of different things you can attempt. This might not be the best option, but it's something you have to try. You will not get better at these identity problems without trying something. You have to make sure that you're willing to attempt to do something. So that's the first thing I could do. The second thing I could do is I could go ahead and force the common denominator. I'm going to write it as CD, as I always do. So in that case, that means I'm going to multiply this side over here by something to make the denominators the same. You'll notice here that I have sine and cosine in the denominator on this side. If I'm trying to force the common denominator, this side right here, this piece, we just need a cosine in the denominator. So I'd put a cosine on top and a cosine on the bottom and make it sine times cosine on that fraction. For this fraction here, I'd multiply top and bottom by sine. Notice again, sine times cosine. And then on top it'd be sine 4 theta times sine of theta. Again, this is a process you can do. I'm not going to do that. It's a valid consideration, it would work, and it would provide us with hopefully the final solution. But anytime I'm dealing with fractions, I like to multiply by my common denominator. I think it's a little bit more efficient, it gets to the point, and it simplifies so we don't have any fractions that we actually have to deal with. So in that case, I'll notice here that my common denominator for this problem is sine times cosine. Specifically sine of theta times cosine of theta. And yes, it is important that I make that distinction, because there are 4 thetas and 5 thetas in here that could cause problems. The way that I found that common denominator is the same way that I find all my algebraic common denominators. The bottom here is sine. I'm going to take that with me. The bottom here is cosine. I'm going to take that with me. And I'll notice that when I look at this third fraction, I already have sine and cosine together. I don't need to take anything from this one. So now what I'm going to do is I'm going to write this step out in its most obnoxious form. I'm going to write every single fraction in this problem to be multiplied by the sine of theta cosine of theta. The reason for doing this is because I am only allowed to multiply both sides by the exact same thing. So in that case, I have to multiply not only the tops of the left side, but all the tops of the right side. Technically, this right here was sine theta cosine theta times the whole thing, and then it got distributed to both those pieces. So in this case, you'll notice with this fraction right here, don't be terrified of these fractions. They're not scared. They're not scary at all. Sine of theta on top can cancel out with sine of theta on the bottom. Just like if I had an x on top and an x on the bottom. The same argument can apply here, cosine of theta divided by the cosine of theta. They can cancel out because, again, it's like I had an x here and an x here, and one on top, one on bottom, they can cancel each other out. Heck, if you don't want to use x's, use 5. This is 5, this is 5, now that 5's cancel out. Same thing I can do here. The only thing I can't do is I can't try and cancel out theta with theta, because they're on the insides of trig functions, and again, based on our rules, we can't manipulate the insides with the outsides. So this being on the inside of a trig function, this is on the inside of a different trig function. This is technically, I have to go inside to outside and then outside to inside to manipulate the thetas. It's not the theta canceling out, it's the entirety of the sine of theta canceling out, as is the cosine of theta canceling out with this one. Okay, now with that being said, I am left with the cosine of theta times the cosine of 4 theta minus the sine of theta, the sine of 4 theta, equals to the cosine of 5 theta. Now again, this is where your comfortability of playing with the identities will help you conclude this problem. I know right now that I'm done. The reason why I am done is because this side over here, as I can recognize, I'm going to scroll back up, is nothing more than this identity here. The cosine of x plus y, such that I have cosine x, cosine of y with a minus sign for the sines. So down here, one more time, cosine of x, cosine of y, minus sine of x, sine of y. So in that case, this side here is nothing more than the cosine, because the cosines group and the sines group and the minus sign is there. And again, the sine identity for sum and difference holds the sign to be constant. So with this being a minus sign, it's going to be theta plus. It's going to alternate that sign for theta. And then therefore, this should be quite obvious that that is done, because I can combine 1 theta plus 4 theta.